recording. Yes, we can talk about how to set up the lockdown browser during the laboratory session. Okay, so just to check that everything is all set, can everyone see the note sets shared on my screen? Okay, is everyone able to access the note sets? Does everyone see where on Canvas that you're supposed to pull the note sets from? Okay, perfect. So then I'm going to switch to tablet view, and now we'll discuss chapter 1. So this is an introductory chapter covering matter and measurements. So let's get started. These are some objectives. You'll see these covered throughout the chapter, and these are some goals that you want to have. By the end of the chapter, you should be able to do or complete any task outlined in these objectives. So let's look at matter. So first and foremost, your goal is to be able to describe states of matter from the macro scale and particulate perspective. So what do we mean by that? So chemistry, what is chemistry at a fundamental level? It focuses on the study of the composition, properties, and the transformation of matter. And matter, quite simply, is anything that takes up space, has volume, and has mass. So it's a pretty catch-all category. Now, in terms of states of matter, we're going to look first at the macro scale perspective. So when we say macro scale, that these are bulk materials that we can see and manipulate. So the things that we interact with fundamentally on a day-to-day basis. This is the domain that we can see and readily observe without external assistance. So if we think about a solid for a moment. So solids, they have a fixed shape and a fixed volume. So this cube has a fixed shape. It's not changing in shape. It's not dynamic based on the container. And it has a fixed volume. It occupies a discrete amount of space. Your liquid has a fixed volume. However, as we know, if we try to pour ourselves a glass of water, the liquid will adopt the shape of the container. Depending on the exact shape of the container, the liquid will adopt a slightly different shape. It still has the same volume. It's still taking up the same amount of space, but it just has a different shape. Now, a gas is pretty interesting. So if you take a gas and we just look at a macro scale view of the gas, it adopts the volume and the shape of the container. If we uncork it and we just leave our beaker containing our gas in the room, suddenly the gas will fill the room. So if we uncork this container, for example, yes, for those who are asking, yeah, the way I set it up, in order for me to have the tablet in drawing mode and to show you some figures, that you won't be able to see my face, but if you want to ask questions, I'm still able to respond, and I will be shifting it up so we can talk and you can see my face later on in the lecture. But when I'm writing on my tablet, I like to keep it steady, just so that way I can show you some figures via the camera, show you how to enter things into your calculator. But yeah, did that address that question? Perfect. Okay. So we're now going to move from the macro scale view to the particulate scale. And this is really the domain of chemistry. So if we look at matter from the microscale or particulate perspective, and we really begin to ask, how are the particles arranged in each state of matter? So the particulate scale, we're primarily dealing with atoms and molecules. We're looking at things from the atomic or molecular perspective. So for the solid, if we look at our zoomed in view, if we look at the individual atoms or molecules in a solid, the particles are closely packed and they're vibrating in place. So there's not a lot of molecular motion in a solid. There is still molecular motion, the particles are still shaking in place, but there's not a lot of it. For the liquid, the particles are loosely packed, and as a result, they're able to slide past each other. So there is a greater degree of molecular motion. There's a greater amount of freedom of motion in a liquid. And this is why a liquid is able to adopt the shape of the container. The particles are not held as rigidly in place via intermolecular interactions. So for the gas phase, the particles are heavily dispersed and these particles are rapidly moving. So if we think about, we draw some arrows, these particles are just rapidly bouncing about and they're not particularly associated with each other. So if we go from a solid to a liquid to a gas, we see that the degree of molecular motion increases and how closely and tightly our particles are packed has decreased. Any questions so far? So this is a good example of how chemists think. We look at matter and we try to look at the fundamental components that make up matter. And by understanding the fundamental components and the behavior of these fundamental particles, we can understand the behavior of bulk materials. So let's look at atoms, molecules, and elements. So our goal in this section is to classify matter as atoms, molecules, or elements. So matter is composed of atoms. So atoms are the fundamental building block that we look at when we talk about chemistry. And atoms will bond together to form molecules. So the central doctrine, in my opinion, of chemistry is that the composition of matter determines the properties of matter. So by studying these fundamental particles that make up matter, we can understand the behavior of matter. So let's start off with our first major building block of matter, the atom. So the atom isn't the absolute smallest unit of matter, but it is the smallest unit of an element that has the properties and reactivity of that element. I like to think of atoms as the smallest functional unit. Sort of contradictory to its name, which based on Greek means an indivisible particle. So what do I mean by smallest functional unit? So if we think about a block of sodium, so if we think about a block of sodium solid, for example, if we take this block of sodium and we put it in water, we would quickly see a fire. Now, sodium reacts with water on a bulk scale. If we look at a sodium atom, so if we look at our sodium atom, and we decide to react it with a water molecule, so let's draw that out. We would expect to see a reaction. We would expect to see a reaction. The atom is the smallest unit of an element that has the properties and reactivity. Bulk sodium reacts with water. Sodium atoms react with water. Now, the reason why this is important is the idea of half an atom doesn't make any sense. Once you start breaking the sodium atom into further fundamental pieces, it ceases to behave and act like sodium. So the atom is the smallest functional unit of an element. Does that make sense to everyone? Any questions on this idea? Okay, let's keep going then. So a molecule, quite simply, is the smallest unit of a pure substance containing, and this is really important, 2 or more atoms bonded together. So this is our criteria for a molecule. So for example, we can look at an oxygen atom. So we just have one oxygen atom. And if we take two oxygen atoms and stick them together, let me draw this a little bit more clearly. So this is O2, and this is an oxygen molecule. So as long as we have two or more atoms, we're dealing with a molecular species. Now, what's really important is that they're chemically bonded together, and we'll talk what that means in more detail in later chapters. So, an element, and elements are fundamental building blocks of matter. It's a pure substance that cannot be chemically decomposed to its component elements. Now, this seems like an odd definition at first glance, but this really stems from chemical history, where when we were investigating and trying to identify and isolate elements, we often had to rely on empirical methods. Does this sample decompose into a known element? Can I decompose the sample into a known element? So to give you an example of this, if we take hydrogen gas, no matter how hard you try, so let's look at H2, this is hydrogen gas. No matter how hard you try, you can't, through chemical means, generate a simpler component element. You start with hydrogen, you'll end, if you're trying to generate elements, with hydrogen via chemical means. Sure, I can post the written notes on Canvas. That's more than okay. So quite simply, an element is a pure substance that cannot be decomposed into its component elements or a simpler component element. So to contrast this and to really show you the difference between an element and what we call a compound, if I take water, for example, and I really apply a strong electric current, I can generate hydrogen and oxygen gas. So compounds can be decomposed. Elements cannot. Okay, each element has a unique name derived from their isolation, Greek name, or Latin name. Each element has a unique symbol, and there are a few rules with regards to the symbols. The symbols have 1 to 2 letters, and the first and only the first letter is capitalized. So for example, sodium, so Na is known as sodium. The first and only the first letter is capitalized. You may wonder, why is the symbol Na? It's derived from the Greek name of natrium, or sorry, the Latin name of natrium. So sometimes the symbol appears not to match the name. That's because some of the element symbols are derived from historical names. Now, to really show you why you need to be careful with these capitalization rules, capital C lowercase o is cobalt, while capital C capital O is carbon monoxide. So notice if we have 2 capital letters back to back, we have 2 elements in a compound, because each of these capital letters are representing a unique element symbol. So make sure you follow the capitalization rules so that way you don't end up confusing someone reading your chemical formulas. Any questions so far? Any questions so far? If not, let's keep going then, and let's look at elements and the periodic table. So your goal in this section is to be able to classify elements as metals, nonmetals, or metalloids. And the reason why we're bringing up this topic relatively early is that there are a lot of rules that you can unpack and utilize if you understand what elements are metals, nonmetals, and metalloids. Okay, so one thing I want you to point out, and I just want to stick in the back of your mind, is that Hydrogen is a bit of an oddball. Hydrogen is a non-metal. Okay, even though it's traditionally on the metal side of the periodic table, hydrogen is a non-metal. Okay, we'll use that fact in a moment. So let's talk first about our metals. So what are metals? So metals, in terms of properties, they're shiny, they're ductile, and they conduct heat and electric current. So metals are primarily located in the bottom and the left side of the periodic table. And as we can see very clearly, metals make up almost the majority of the element symbols on the periodic table. However, as we're primarily organic beings and we're made in terms of the building blocks and the elements that are responsible for a large amount of biological systems and functions, the nonmetals are king of that domain. Nonmetals are dull, brittle, and they do not conduct heat or electric current. You can think of like a piece of coal, which is carbon. So nonmetals are primarily located on the top and the right side of the periodic table. So as we can see, there are a few elements in the top and right-hand side of the periodic table that are our non-metals. These are the fundamental building blocks of life. Your carbons, your nitrogens, your oxygen, which is the principal component, which is one of the major components of the air that we breathe, as well as our noble gases. Okay, our metalloids, and metalloids are really quite interesting. You can thank them for the function of your cell phone and the chips that make up many semiconductors. They have properties intermediate between a metal and a non-metal. Metalloids are sometimes called semiconductors, as they are principal components of semiconductor chips. Your silicon, which is really the backbone. So metalloids are located in between the metal and non-metal regions of the periodic table. I like to remember my metalloids by this sharp dividing line that is found on most periodic tables. And as you notice, there aren't a ton of metalloids, and they really have these quite interesting and unique properties. Any questions on the major divisions of the periodic table? Your metals, your nonmetals, and your metalloids. Just one exception to keep in mind, hydrogen is a nonmetal, even though it's in a very odd spot in the periodic table. Any questions? So to continue on with this, let's focus on dissecting the periodic table. And this is the type of periodic table that you'll get on the exam. So of course, it's not going to be colored in with metals, nonmetals, and metalloids, but if we're clever, we can make some progress here. So the first thing I like to do is I like to draw my dividing line. I like to draw my dividing line between my metals and my non-metals. And it's nice that it's a nice symmetrical zigzag pattern, as it's really easy to remember. Here we go. So now that we have a rough guideline of our periodic table in place, and I always recommend that you bring a periodic table to lecture, let's try to answer the following question. So which of the following elements are metals? So to help me out on this, where are metals located on the periodic table? Where are metals located? Where are metals located? What side of the periodic table? When I see the word metal, what should I think? And don't be shy to type in the chat or unmute and provide the response. So left, and where else? So left, middle, yeah, that's good. And the bottom of the periodic table. Okay, so let's go through the list. Lithium, so lithium is right here. Is lithium a metal? Yep, perfect. It's on the left-hand side, perfect. What about selenium? Selenium, looking at selenium. Is selenium a metal? No, so we're not gonna circle that. What about cobalt? CO for cobalt, it's right here. Is that in the metal or non-metal section? It looks like it's in the metal section. Argon, AR, right here. Is argon a metal? No, so we'll leave it blank. Boron, now this one's a bit of a tricky one. Is boron a metal? No, boron is a unique subcategory, it's a metalloid. Finally, let's look at calcium, Ca. Is calcium a metal? Yep, perfect. Okay. So let's now do this next exercise. Which of the following elements are nonmetals? Okay, so in terms of nonmetals, let's look at nitrogen, N. So looking at nitrogen, is nitrogen a nonmetal? Is nitrogen a nonmetal? Yes, so we'll circle it. Carbon's a bit of a freebie. Is carbon a nonmetal? If we go and find carbon, is carbon a nonmetal? Yep, okay, so we'll circle carbon. Sulfur, is sulfur a nonmetal? Yeah, looks clearly in the nonmetal domain. Chlorine, let's look at chlorine, Cl. Is chlorine a nonmetal? A lot of yes responses, yeah. What about aluminum? Just to make sure everyone's paying attention. If we look at aluminum, is aluminum a nonmetal? No, so we'll leave it blank. And then finally, helium, He. Oops, let's zoom in really quickly. Helium is in fact a nonmetal. It's on the right-hand side of the periodic table. Okay, perfect. So far, so good. So now let's try to answer the next question. So from the list, we need to select each metalloid in the previous two lists of elements. So if we've already assigned something as a metal or non-metal, we don't have to think too much about whether it's a metalloid. So let's look at all the elements that we have not assigned so far. So selenium. So looking at selenium, is selenium a metalloid? Is selenium a metalloid? Let's look at selenium. Is selenium a metalloid? So let's check. So if we go to our table and we look and see, is selenium a metalloid? As we see, it's actually a non-metal. So we'll leave selenium blank. Okay. What about argon? Ar. So is argon in the metalloid section of our periodic table? No. Okay, so we're good to go there. What about boron? So looking at boron, is boron a metalloid? Yes, it's clearly in the metalloid section. So just to shade things in, if I was taking an exam, this is what I would do. Almost immediately, I'd start shading in some of the major metalloids, just so that way I don't forget. And boron clearly is a metalloid. Finally, let's check on aluminum. Is aluminum a metalloid? Is aluminum a metalloid? Let's check at aluminum. Nope. Okay. So it looks like we got all of them. So this is an example of a guided example where we've worked through this example as a class. Now what I'm going to do is I'm going to ask everyone to take a few minutes and I'd like everyone to tackle the following problem-solving session. And you're more than welcome to submit your responses using Canvas Quiz 1.3. So you're not required to immediately submit your responses, but I will be monitoring and checking your responses to get a sense of how everyone's at in the class. So let's take a few minutes and let's work on these 3 problems. So in the first one, you identify the metals. Second one, you identify the non-metals. And the third problem, you identify the metalloids. And if you like, you can message me your response for question 1, 2, and 3 by including the number in front of your responses. And don't be shy to ask questions or submit your response. And we'll discuss in about, let's say about 3 minutes. And don't be shy to submit your proposed responses. Yep, exactly. It's under quizzes 1.3. And I'll be checking to see how everyone's doing. But don't be shy to just message me your proposed responses using the chat function, either privately or publicly in the chat function, just so that way I can get a sense of how everyone's doing working through these problems and how comfortable everyone is on these problems. Sure. So I'm getting a few responses for question 1. So let's try to get about 1 more response. We'll discuss this set in about 2 more minutes. And don't be shy to message me your posed responses using the Canvas chat function.
Hey, Professor.
Yes.
So you want us to complete these quizzes as we're going through the lecture and just submit them?
Or you, yes, ideally, or you can record your responses in the notes and then complete the quizzes afterward. Whatever,
Okay.
whatever is convenient for you.
So it's not due like right now, in other words?
No.
Okay, cool.
But I do check people's responses just to guide what feedback I provide.
Is there a due date like for it?
Yes, they'll be due at the end of the week.
Okay, cool. Thank you.
Yep, no problem at all. Okay, I see a lot of reasonable responses for question 1. So let's talk about this as a group. So if we go to our periodic table and we look at beryllium. So is beryllium in the metal section? So is beryllium in the metal section of our periodic table?
Beryllium is?
Yep, so
No.
we'll circle that. Okay, what about Te, tellurium? Not a fun compound to work with, smells terrible. Is that in the metal or non-metal section? So tellurium, is it a metal or non-metal?
It is a metalloid?
Yep, so it doesn't fall under our metal category, so we'll avoid circling it. But I'm just gonna put a little note that we think it's a metalloid. What about iron, Fe? Is iron a metal? Yep, so we'll circle it. Okay, what about neon? Neon, which is right here. Is neon a metal? Nope, so we'll leave it blank. Okay, and this one's a bit of a trick question. Is hydrogen a metal? Is hydrogen a metal? No, so you leave it blank. It's a non-metal. Finally, potassium, K. Is potassium a metal? Yep, so we'll circle it. Perfect. Let's work through the non-metals now. So we're asked which of the following elements are non-metals. So let's look at phosphorus first. And looking at your own periodic table, I'd like you to tell me, is phosphorus a metal or non-metal?
Non-metal.
Yep, so we'll circle it. Let's look at arsenic now. And this one we'll have to take a close look at the periodic table for arsenic. Is arsenic a non-metal or is it something else?
Falls under a metalloid.
Yep, exactly right. So we'll just make a note that it's a metalloid. Oxygen, is oxygen a non-metal?
Yes, it's a non-metal.
Yep, so we'll circle it. And what about fluorine? And let's get a few responses in the chat. Is fluorine a non-metal? Yep, so we'll circle it. CS or cesium, is cesium a non-metal? Keeping in mind that cesium is all the way over here in our periodic table. Nope, cesium is clearly a metal. Okay, so we'll leave it uncircled. And what about krypton? Kr, all the way over here. Is krypton a non-metal? So I see some responses in the chat, and you are correct in that krypton is in fact a non-metal. Perfect. Now, from the above lists, let's try to select our metalloids. And you're more than welcome to provide your responses via chat or verbally using the voice chat feature in Canvas. Both are more than okay. Metalloids are their own unique category as they behave slightly different than your typical metals and non-metals. So let's select each metalloid from the previous two lists. So we said that tellurium, we suspected tellurium is a metalloid. So we'll circle tellurium. We looked at arsenic and we said arsenic was a metalloid. Perfect. What about neon? Is neon a metalloid? Is neon a metalloid? What do we think of neon?
Neon is a non-metal.
Yep, it's a non-metal, so we'll avoid circling it. Hydrogen we said is a non-metal, and cesium we said is a metal. So we check off tellurium and arsenic, a pair of not very pleasant elements to work with. Now, what is the purpose of all of this? Why did I have you identify metals, non-metals, and metalloids? Well, that leads in wonderfully to the next idea, which is our next way of classifying elements, which are groups, periods, and the periodic table. So the periodic table is a central organizational structure that we use to understand and sort elements based on their properties and reactivity. So in this section, given an element symbol and the name, you're going to identify the group name, group number, and group properties. So the periodic table, the elements aren't just arranged randomly. The periodic table is organized into two major organizational schemes, groups and periods. So we'll talk about periods first. So a period is a row of elements arranged in order of increasing atomic number and atomic mass. So this number on the left-hand side of each row is our period number. This number will have a little bit more significance once we cover electronic structure. Now, for now, the real shiny accomplishment of the periodic table has to do with the organization of elements based on groups. These groups are columns of elements with similar properties and reactivity. So anytime you see a vertical column in the periodic table, each vertical column has a number and a name, and we call this a group. So this number above each column is known as the group number. And you want to pay special attention to the group number as it allows you to shortcut through many calculations and processes in terms of predicting element charge, predicting compounds that can form from each element, etc. So you may notice already that there are two different letters at play, A and B. So this A symbol indicates that we're dealing with a main group element. These are found on the left and the right hand side of the periodic table, while this middle group of elements with the B symbol or B group letter are our transition metals. And transition metals have to be handled differently than your main group elements, as transition metals can adopt variable charge and they really have quite interesting properties. So just as a reminder, main group elements have a group letter A. Transition metals have a group letter B. Now, if we delve into the periodic table in more detail, let's talk next about our named groups. So what is a group fundamentally? A group is a column of elements with similar properties and reactivity. And there are a few named groups that we should know and be familiar with, as they are quite famous or infamous. So your named groups, your group 1A elements are known as your alkali metals. These are highly reactive metals and they're known typically as great electron donors. You dump lithium into water or you mix lithium with many nonmetals and you'll observe quite a vigorous reaction. Contrasting that are your alkaline earth metals. These are your group 2A elements. They're called alkaline earth metals because they're water reactive metals that generate an alkaline, otherwise known as a basic solution, when dissolved in water. So if you're curious, whenever you dissolve magnesium oxide or calcium oxide in water and you observe that it's basic, it stems from this property. Halogens. Halogens are a pretty infamous group of elements. They've certainly killed a few more chemists than we can count trying to isolate them, especially fluorine. They're strong oxidizing agents, great electron acceptors, and they're pretty dangerous. You won't be handling pure halogens in your boxed lab kit, that's for sure. So halogens are your 7A elements. Now, another important group are your noble gases. They're group 8A elements. These are relatively unreactive and inert gases. I have to put the disclaimer relatively because with enough reactive enough agent, you can get noble gases to react, but generally noble gases are pretty inert, unreactive. That's why they're often used as carrier gases or to blanket chemical reactions to minimize reactions with oxygen. So group 8A elements are your noble gases. You see noble gases referenced a lot in rules with regards to predicting charge, predicting chemical bonding. So these are the groups that I'd like you to be familiar with by name. Okay, so here's our exam periodic table once again, and I'm going to just go through and I'm going to put my group numbers in immediately. Remember, you skip your noble gases when you write your main group element group numbers. So you skip your transition metals. So these are your transition metals, which are the B group elements and are not counted when you're numbering your main group elements. Okay, so now that we have our group numbers clearly indicated, let's put out our period numbers. Okay, and now we have a workable periodic table. This is the periodic table that you'll be provided for all exams, and it's one that I want you to be familiar using for all exams. The reason being is that this is very similar to the periodic table provided on the ACS. This is the IUPAC periodic table, which is pretty standard for most exams and courses in chemistry. Ah, yes, yeah. Sure, I can definitely make that change. I'll also be providing full credit for completion, but I can set them the problem solving sessions to unlimited attempts. I'll do that shortly after this lecture. Okay, so now that we have our periodic table numbered, let's now, just one moment. Let's now go and let's try to answer these questions. So in this first guided example, we want to identify the group number and group name for each element. So let's look at Br, otherwise known as bromine. So looking at Br for bromine, if we look at our periodic table, what group number is bromine? What group number is bromine? Would anyone like to volunteer the group number for bromine? Either, okay, perfect, 7A. And what do we call group 7A elements? What do we call group 7A elements?
These would be the halogens?
Yep, exactly right. So bromine is a halogen, perfect. Would someone else like to, or would the same person like to volunteer a group number and group name for neon? (8A), yep, that's exactly right. And we call that a member of the noble gases. Perfect, perfect. So far, so good. So let's try to answer this next question. We're asked, what is the atomic symbol for a period 2 group 5A element? So let's go through our periodic table. So we're looking for period 2. So let's circle that. Okay, group 5A. Okay, so what element meets those two categories? Period 2, group 5A. That would be nitrogen. Yep. Okay. So let's keep going with this. And now we're asked to identify which two elements have similar properties. So what do I mean by similar properties? What are we looking for fundamentally when I say similar properties? The periodic table is organized in terms of groups with similar properties. So two elements with similar properties will be in the same group. So which pair of elements are in the same group? Which pair of elements are in the same column?
Bromide and iodide?
Exactly right. Bromine and iodine. Yep. They're both group 7A elements. So if we go up to our periodic table, we clearly see bromine and iodine are in the same group, same column. So they'd have similar properties and reactivity. Okay. So let's now work on a problem solving session. So let's take about 3 minutes to work through the following problem set. So you're asked to identify the group number or group name for each element. I'd like you to tell me the atomic symbol for a period 3 group 6A element. And then I'd like you to tell me which of the following elements in the list have similar properties. And you can message me your responses or input your responses into Canvas quiz 1.4. And we'll spend about 3 minutes working on this problem solving set. And then we'll come together as a group to discuss in about 3 minutes. Don't be shy to message me with questions or your proposed responses. So I see a lot of reasonable responses for the first question. So magnesium, if we go to the periodic table for magnesium, just one moment, we see that magnesium is in group 2A, and we call these elements the alkaline earth metals. Okay. Looking at carbon. So looking at carbon, it's a group 4A element. Let's spend some time working on parts 2 and 3, and we'll continue our discussion in about 1 to 2 minutes. I'm seeing a lot of reasonable responses in real time, so thank you for participating. It's certainly helping me get a sense that everyone's doing quite well so far. So let's discuss part 2. So what is the atomic symbol for a period 3 group 6A element? And I see a lot of people commenting sulfur, and that's exactly right, but let's show the logic behind it. Let's try to understand why that is. So if we add our period numbers, 1, 2, 3, we add our group numbers, our period 3 group 6A element, that matches sulfur. So we'll put the symbol for sulfur, which is S. Let's now look and try to identify which 2 elements in the following list have similar properties. So which 2 elements have the same group? And don't be shy to submit your responses via chat. Phosphorus and arsenic. Yep, exactly right. So if we look at the periodic table for phosphorus and arsenic, both phosphorus and arsenic are group 5A elements. Exactly right. Very good. Perfect. Any questions on this example? If not, let's keep going. So let's talk next about atomic and molecular elements. So your goal in this next section is to be able to write a valid chemical formula for an element, given its symbol or name. Don't worry about it. You'll get credit. Don't worry about it. It's for participation. If there are small formatting errors, you'll still get points for the problem solving. So elements can be either atomic, consisting of a single atom, or they can be molecular, where they're comprised of two or more atoms. So your atomic elements, single atom, are your metals or your noble gases. So let's give an example of each. Would someone like to volunteer? What is an example of a metal that you'd like us to write? What's an example of a metal? Any metal. Can be the name or the symbol. Gold, sure. With the symbol AU, Orium. Yep. So gold exists as an atomic element. What's an example of a noble gas? So gold is our representative metal. What would an example of a representative noble gas be? An element in group 8A. Neon, sure. Yep. So neon is our representative noble gas, which remember is group 8A. And neon also exists as an atomic element. Single atom. Okay, let's now look at our molecular elements. Let's now look at our molecular elements. These are nonmetals and our metalloids primarily. Now, we have to be a little more specific when we talk about molecular elements. There are two major subcategories. Diatomic, di meaning two. There are molecular elements that are composed of two atoms. These are your halogens, oxygen, nitrogen, and hydrogen. So for example, oxygen, if someone just says oxygen or they give you this symbol for your element, the correct formula for oxygen would be O2. So when someone says oxygen, they're referring to O2 gas. So we have two atoms of oxygen in one molecule of oxygen. Okay, what would an example of a halogen be? What would an example of a halogen be? Let's have a representative halogen. Chlorine, sure, that's perfect. So chlorine, Cl. So we have C, it really corresponds to Cl2 gas. So this is our good old friend chlorine. And we have two atoms of chlorine in one molecule. Okay, so we're slowly starting to develop the ability to write formulas from the element name. Okay, the other subcategory of molecular elements are our polyatomic elements. These consist of three or more atoms. These are sulfur and phosphorus. So for example, S8, sulfur consists of 8 sulfur atoms per molecule of sulfur. So this is the chemical formula for sulfur. Well, for phosphorus, it's P4, which consists of 4 phosphorus atoms per molecule of phosphorus. We won't worry too much right now about the exact connectivity. I just mainly want you to be able to recognize and write the formulas for most of your common elements. Any questions on this example? Okay, if not, let's keep going now. And let's talk about the physical states of elements. Let's talk about the physical states of elements. So your goal in this section is given an element symbol or name. You should be able to write a valid chemical formula for that element with the correct physical state. Okay? So the state symbol indicates the physical state of each substance. S for solid, L for liquid, G for gas, AQ for aqueous, which means dissolved in water. Aqueous is primarily used when you're describing mixtures, not pure substances. So in terms of metals, it's a nice short and sweet rule. Metals are solids at room temperature, overwhelmingly. There's only one exception, and that is mercury. So mercury is a liquid. Your non-metals are a little bit more nuanced. So for your non-metals, your noble gases, sort of obviously, hydrogen, nitrogen, oxygen, fluorine, and chlorine are your gases, which have a G symbol. So for what would an example of a noble gas be that's not neon? Let's pick a new one. What's a new example of a noble gas? Noble gas that's not neon. Argon, sure. So argon, we'd put the gas symbol. Just like hydrogen, we'd put the gas symbol. Just like nitrogen, we'd put the gas symbol. Oxygen gets the gas symbol, etc. In terms of liquids, bromine is a liquid. So we'd write it as Br2, liquid. And as a general rule, if it's not on any of these lists, most other non-metal and metalloid elements are solids. So for example, iodine is a solid. The goal of this portion is really to get you familiar with the natural physical states that elements exist in at room temperature, so you can begin to help visualize and understand what each of these element symbols represent in our physical world. So let's do some examples. So in this following example, we're asked to write the formula and physical state for the following elements. So this will be a guided example that we'll be working on together. So first, Na, so that's sodium. I already have the formula. But what do we know about sodium? What do we know about sodium that's going to help us write the physical state? What's so special about sodium? What can help us out here? Sodium is what? What's so special about sodium? It's a metal. Yep, exactly. So then, metals, what state symbol do we put? Solid. Yep, perfect. Okay, oxygen. Let's look at oxygen. So, what's so special about oxygen? What type of element is it? Is it atomic, diatomic, polyatomic? What is it? Oxygen is diatomic. So we'd write oxygen as O2. Now we're going to have to think a little bit because oxygen's a non-metal. What state symbol is oxygen? Consider that it's the principal, one of the major components of the air that we breathe. It's a gas. I always like to have an intuitive link when I think about state symbols. So hydrogen. So what's the deal with hydrogen? Is it atomic, polyatomic, diatomic? What is it? Hydrogen is diatomic. So we'd write it as H2. And then what state symbol do we put for hydrogen? Gas. Yep. Perfect. Sulfur. What's the deal with sulfur? Would someone like to volunteer the formula for sulfur? This is one of the tricky ones that you may have to memorize. So sulfur is actually one of our exceptions. It's a polyatomic element and has the formula S8. Yep, exactly. And if we had to guess a state symbol, let's pretend we didn't know the state symbol. If we had to guess, what's a pretty good guess for the state symbol of most elements? If it's not on any of our lists, we guess that it's a solid. S8 is pretty interesting and it's a super bright yellow solid. It smells terrible, not very fun to work with. Okay, any questions on this example? It's mainly just helping you recall via practice and helping you integrate the idea of correlating element names with formulas with the correct states. To test this, we're going to do a quick problem solving session. This is Canvas Quiz 1.6, and I'd like you to write the formula and physical state for the following elements. And in Canvas, you're selecting from a drop-down menu, and I'll check to see how everyone's doing on Canvas Quiz 1.6. So we'll spend about 2 to 3 minutes on this. This should be pretty fast. And you're more than welcome to message me your proposed responses for each of these 4 parts in the chat feature. And don't be shy to propose in the chat a proposed formula with a state symbol for any of these 4 categories. Or feel free to ask questions. This is mainly a way to help people actively practice the material. And we'll discuss in about 2 minutes. So the diatomic I provided in the list. These are hydrogen, halogens, oxygen, and nitrogen. Your polyatomic are sulfur, which is S8, and phosphorus, which is P4. It's in the list on page 11. Did that answer your question? Perfect. So taking a look, we have a few responses on Canvas. And I see a few responses in the chat. So I see a lot of reasonable responses for our first part. So barium. So barium is Ba. It's a metal. So metals are typically atomic and solid elements. So we'll write the formula for barium is Ba solid. I see some responses for bromine, so let's talk through bromine together. So bromine, is it a metal, non-metal, and what's so special about bromine? Is it atomic, diatomic, or polyatomic? What's so special about bromine? It's a halogen, yep, it's a 7A element, so it's diatomic. So we write this as Br2, okay? So we have the formula right so far. Now, what's so special about bromine? What state symbol did we mention for bromine? This is one of our exceptions. It's a little weird, so it's a liquid, yep. And this idea of writing formulas with state symbols will be really invaluable for later chapters, and it really helps you understand when you're in the lab and you look at a chemical, what is it? You know, that liquid probably is going to be bromine if it's labeled bromine. Let's look at xenon next. So xenon, what is special about xenon? What's its group, and is it atomic, diatomic, or polyatomic? Xenon is a noble gas, and what does that tell us? What does that tell us? Is it atomic, diatomic, or polyatomic? It's a noble gas, ergo it is. Noble gases are atomic, just a single atom. So we'd write it as Xe. The halogens are diatomic. Now, what state symbol should we put for the noble gas? I know this seems, yeah, gas. Perfect. It's in. Thankfully, the noble gases are easy to remember because it's in the group name, which is why I have everyone memorize the group names. Let's look at phosphorus. So phosphorus is one of the special ones. So what is the formula for phosphorus? What is the formula for phosphorus? P4, exactly right. And so phosphorus is polyatomic. And what state symbol do we put for phosphorus? What state symbol do we put for phosphorus? Solid, yep. If you had to take a guess, most elements are solids. Okay, perfect, perfect. Any questions on this example? It's mostly recalling what we discussed from the earlier page, and it may take a while and a little more practice to get familiar with all of these names, formulas, and state symbols, but it's best to start now so that way you're prepared for later chapters. Any questions before we move on? If not, let's keep going then. So our next goal in this section is to identify elements and compounds. So let's talk a little bit about what is an element. Whoops. Yes, you are able to. Mm-hmm. Mm-hmm. So an element, quite simply, is a pure substance that cannot be chemically decomposed to its component elements. So for example, if you take hydrogen gas, no matter how hard you try, the best you're going to do is recover hydrogen gas. You're not able to get a simpler component element. You're not able to convert hydrogen into another element via chemical means. A compound, however, is a substance that can be chemically decomposed to its component elements. So let's look at a classic example of table salt. Here we have sodium chloride, and I'm going to write it with each of the elements having a different color. So sodium chloride solid. If you apply an electric current, you can initiate a chemical decomposition where your sodium chloride decomposes to yield elemental sodium and elemental chlorine. Where we have successfully taken a compound and decomposed it in a chemical reaction to pure elements. So then we'd say, because sodium chloride can be decomposed into pure elements, sodium chloride is a compound. Does this idea make sense to everyone? A compound can be chemically decomposed. Okay, so another definition of a compound is a substance containing two or more different elements covalently bonded. Or rather than covalently bonded, or bonded via an ionic bond. So the difference between a compound and a molecule is a compound contains two or more different elements, while a molecule just contains two or more atoms. Does that make sense? Perfect. So let's talk next about ionic and covalent compounds. So compounds can be classified as ionic or covalent. So an ion, so if we're talking about ionic compounds, let's define what an ion is. An ion is a positively or negatively charged atom that we call an atomic ion, or a molecule, which is a polyatomic ion. So let's give an example of each. So for example, potassium plus, where this plus symbol is signifying the charge. This is an atomic ion. Cl minus is also an atomic ion. For a polyatomic ion, let's give an example of that. And that this is a molecule with a net total charge. So for example, carbonate would be called a polyatomic ion. It is a molecule, a set of atoms covalently bonded with a net total charge. Now, ionic compounds, as their name implies, are a compound comprised of a positively charged cation and a negatively charged anion. Overwhelmingly, when we talk about ionic compounds are typically composed of a metal cation and a non-metal anion. So for example, sodium chloride is composed of sodium cations. This sodium is our cation, and chloride anion. This chloride is our anion. Of course, the charges don't just have to be +1 and -1, but the main thing I want you to keep in mind Ionic compounds are typically composed of a metal cation and a non-metal anion. So the presence of a metal is a signpost that you're dealing with an ionic compound. Now, one special sort of nomenclature that we use when we talk about ionic compounds is this idea of a formula unit. The formula unit is the smallest repeating set of ions in an ionic compound. And quite simply, when you talk about formula units, you can think of it as the simplest set of atoms in your ionic compound. So for example, sodium sulfide, which is Na2S. Again, we have our metal. So we have sodium plus, we have 2 sodium plus ions. And then we have our non-metal, which is sulfur. So then we have 1 S2 minus anion. So the formula unit, I like to think of it as a single, simplest molecule of an ionic compound. Often when you're dealing with problems that reference formula units, you handle the calculation similarly to how you'd calculate the number of molecules of a compound. Okay. We'll talk more about formula units towards the end of this class, as there's a lot packed into that statement. The other type of compound that you'll commonly see are covalent or molecular compounds. These consist of 2 or more atoms of different elements covalently bonded together. Covalent or molecular compounds are overwhelmingly composed of 2 or more nonmetals, and most importantly, they are composed of neutral component atoms. So they're neutral with no charged ions. So an example of a covalent or molecular compound would be CO, which is carbon monoxide. And as we notice in this compound, we have 2 atoms of different elements. Now they don't just have to be in a 1-to-1 ratio. We can also have NO2, which has a nitrogen and 2 oxygen atoms. And notice in each case, we have 2 or more non-metals. Does this make sense to everyone so far? Any questions so far? If not, let's do a quick recap. So elements can be either atomic or molecular, and compounds can be either molecular or ionic. So atomic, 1 atom. These are primarily your metals and your noble gases. Molecular, everything else. For your compounds, your ionic compounds contain a metal plus a non-metal, while molecular compounds contain 2 or more non-metals. And what's the critical distinction between an element and a compound? A compound contains 2 or more different elements. So all compounds, by definition, are molecules, but not all molecules are compounds. Okay, so let's do a guided example where we're asked to classify the following pure substances as a covalent, ionic compound, atomic element, or molecular element. So looking at HCl, do we have 2 or more different elements? Do we have 2 or more different elements? Yes, so it's clearly a compound of some sort. Now, if we look at hydrogen and chlorine, are these metals or non-metals? Are these metals or non-metals? nonmetals. So if we have two or more nonmetals, are we dealing with an ionic or a covalent compound? Two or more nonmetals, that's covalent. So this would be a covalent compound. Let's look at P4 now. Is this an element or a compound? Is P4 an element or a compound? It's an element. Now looking, do we have more than one atom? Are we dealing with an atomic or molecular element? Yep, so it's a molecular element. Exactly right. We have more than one atom. Okay, copper solid. Is this an element or a compound? Is this an element or a compound? Element, yep. And do we see is this atomic or molecular? Atomic. So this is an atomic element. Let's look next at calcium oxide. Is calcium oxide an element or a compound? Compound, yep. Now, do we note, looking at calcium and oxygen, do we notice a metal or do we just have nonmetal? Do we notice a metal? So we see calcium is in fact a metal. So is this compound going to be ionic or covalent? If we have a metal, it's going to be ionic. Exactly right. So this is an ionic compound. Perfect. So what I want you to do now as our last exercise for this session is I'd like you to tackle the following problem-solving session, which is going to be Canvas Quiz 1.8. We'll take about 3 minutes and you have 4 compounds, and I'd like you to classify them as ionic or covalent compounds or atomic or molecular elements. And I'll be checking to see how everyone's responding via Canvas and via the chat.
Hey, Professor,
Yes.
could you clarify for me the difference between atomic element and molecular element?
An atomic element is composed of just a single atom in the formula, while a molecular element has 2 or more atoms.
But it has to be the same atom, right? For
Yes, it
molecular?
has to be the same element. Yeah.
Okay, cool. Thank you.
Yep. I'm already seeing a lot of responses in the chat, but we'll give it about a minute and a half more and then we'll discuss. I'm just keeping an eye. I'm also checking the Canvas responses to see if there are any misconceptions I can address. But overall, everyone looks pretty good on this assignment from the responses I've received so far. And we'll discuss in about 30 more seconds, just to give everyone some time. Okay, so let's discuss. So nitrogen triiodide, quite an explosive compound. Oh, I gave it away in its name. Do we see 2 or more different elements? Do we see 2 or more different elements? Do we see 2 different elements? Yep, so it's clearly going to be a compound. Now, looking at nitrogen and iodine, are these metals or non-metals? Are these metals or non-metals? These are non-metals, yep. So then is this an ionic or covalent compound? Covalent compound, exactly. Looking at S8 now, is S8 an element or a compound? Is S8 an element or a compound? Do we see atoms of a single element or multiple elements? Is this an element or a compound? It's an element, yep. And do we see one atom or many atoms? Is this atomic or molecular? Yep, so we have more than one atom of a single element. So this is a molecular element. Yep, let's look next at aluminum chloride. Is this an element or a compound? Do we see two or more different elements? Yep, we see two or more different elements, so this is a compound. Now looking at aluminum and chlorine, do we have any metals present? Do we have any metals present? Yep, so aluminum is a metal. So then is this an ionic or covalent compound? It's an ionic compound. Good, good. Looking at xenon now, is this an element or a compound? Is this an element or a compound? It's an element. And do we see a single atom or multiple atoms? Single, so is it atomic or molecular? It's atomic, yeah. Okay, perfect. So we're at the end of our scheduled lecture session. We'll take a short break and I will see everyone at 12:40 for the laboratory. Let me just pause the recording for a moment. Okay.